Welcome to the third project. In this project, you will create your own ROS service interface and implement it into your code using what you learned from the previous lecture. For this project, you will make two nodes. One node, which acts like a client, which sends a request of an angle to a robot to turn a camera, and another node, which takes in the request and sends back a response, which will be an image the robot takes after moving the camera to the angle specified. Now, since we do not have a real robot and haven't learned about making robots in simulation yet, we're just going to have some pre-taken images which are named by an angle and return one of these images based on the request. These images are available in the resources folder, or you can create your own. It may be helpful to spend some time to think about what message types would be most ideal for our request and response. So let's break down what this project will look like.
For this project, we will create two nodes, a service client node and a service server node. The service client node will send a service request of how many degrees to turn the camera to the service server node. The server will then return the pre-taken image data back to the client. Then, as an added feature, see if you can make your service client display the image for the user to see. In order to complete this task, I will use the OpenCV library, which is a commonly used computer vision library. I will also be using a ROS package called CVBridge, which helps us convert ROS image messages into formats OpenCV can easily use. To use OpenCV and CVBridge for this project, we need to make sure it's installed. Once installed, you will need to include them in your package.xml and cmakelist.txt file to properly include it as dependencies of our ROS package, as well as the individual executables which need them to be compiled. With our package and dependencies configured, we can now use OpenCV and CVBridge in our C++ code. We include them with the following lines, which will give us access to the image C++ data types we will be using, the user interface tools to display images, and then our CVBridge ROS package. To read in an image from a file on your computer, you can use OpenCV's image read function called imread, with a string that has the path to your image. Then, if you want to display an image, you can use the imshow function, which takes in a string to title the display window and the image you want to display. Then we call the wait key function with a value of 0, which means it will keep the display window open until we hit enter. Alternatively, you can put a number value in here for how many milliseconds you want the window to stay open. Now that we know how to work with images with OpenCV and C++, we now have to process them over our ROS service. So we need to convert them into ROS messages to be sent as part of our service response. That is where CVBridge comes in, which gives us the CVImage object, which we can call the toImageMessage method to convert the image into a ROS image message. Then we can convert the ROS message back into an OpenCV image by using the toCVCopy function of the image that gets returned back by our service result. Then one last hint is to use the sensor messages ROS package to utilize this image message we were talking about earlier when creating your custom SRV interface file. If you want to use an interface type from another ROS package, you include it into your SRV file like so, where the data type for the attribute is the name of the package, / and then the name of the interface type. No need to explicitly point to the MSG directory of that package like we do in our C++ code, because ROS knows you can only use messages to create these custom interfaces. Then, of course, be sure to include the package as a dependency for your ROS IDL generate interface command.
This will be a hard project, being that we have not explicitly used OpenCV in this course, which is an external module you may have never used before. But this is exactly how it feels to be a robotics developer. We are constantly solving complex software problems to increase the functionality of our robots. So you need to be able to find resources and existing frameworks which will help you. For those of you who have not used OpenCV before in C++ projects, I will quickly go over how to include it into your project right now. Any of you who have used OpenCV before and are confident in your CMake skills can go ahead and pause here and try this project out.
First things first, let's make sure we have OpenCV installed. On Ubuntu, we can do that with the following commands.
Then you can easily check your OpenCV version with the following command. So here we see the version I have is 4.5.4. Don't worry if you have a higher version number. Next, I want to make sure I have the CV Bridge ROS package installed. You can install it like so. Now, most of you will actually have CV Bridge installed by default if you followed along with me in the ROS installation lecture, but it was worth mentioning in case you didn't have it for some reason. Now, going back to OpenCV, you may be curious as to where OpenCV got installed on our Ubuntu machine. So we can go over to Computer, and the files we are interested in are under User, Include, and then we will scroll down to OpenCV4, or if you're watching this way into the future, this may even say OpenCV5, depending on your version number. Then I can go to the OpenCV2 directory. It's called this because the original OpenCV was built for C code, then it was adapted for C++ in OpenCV 2.3, so they just kept the name as OpenCV2 for backwards compatibility. But here we see this is the location of all the header files we will need for our C++ code. So we have some header files here and some organized into different folders, which means it'll be beneficial to add this directory path to our C++ VS Code extension. So if I right click on one of these files, click on properties, I can get the parent folder. I'll copy it. So now I can go into VS Code and I will hit F1 to bring up the command bar, and I will type C++ edit configurations, and here I'll click the UI one. Scroll down to the include path section, and I will just paste it at the bottom, and then add these 2 star characters to tell VS Code to look through this directory recursively to find all of our related header files. Great, so now you are all set to code your C++ code to utilize the OpenCV library and have it do things such as autocomplete. Now let's head over to our cmakelists.txt file to see how we can include it there. I already mentioned that I plan on using the image message type from the sensor messages ROS package, so I will include that along with OpenCV and the CV Bridge ROS package. Then, in order to use messages from other packages in your own custom interfaces, you need to include them as dependencies within the ROS IDL generate interfaces call. So in this case, I plan on including the image message from the sensor messages package, so I include the package as a dependency like so. So that should do it. So I can go ahead and save this file. And as always, you should always include any new packages that you include in your cmakelists.txt file as dependencies within your package.xml file. And as always, be sure to save it. Alright, with that OpenCV prep out of the way, it's time for you to try this project out on your own. So go ahead and download the sample images from the resources section of this lecture. Then make your custom service, which will allow you to request a degree for the camera to turn, which responds with an image. Then, with the help of OpenCV, create a service server which will take the request and return an image from the sample images, as well as a service client which will be used to make the request, and as an optional challenge, display the image returned in an OpenCV window. With that, pause the video and give yourself an hour or so to try and complete as much of this project as possible on your own. Alright, how'd it go? I'm sure this was a hard project, being that you had to use OpenCV, and we have not explicitly covered it in this course. But this is exactly how it feels to be a robotics developer. You may have also been able to achieve the same result with a different framework or your own custom solution. But as a developer, you always need to balance how to incorporate advanced functionality into your robots as quickly as possible. I will go ahead and walk through how I would approach this project. In order to do this project, make sure you have the downloaded images from the resources section. Here I have gone ahead and downloaded it and unzipped it here onto my desktop.
So here are the 5 images in case you were interested in looking at them. So I'll just go into my package directory and place the images there. Okay, first thing I will do is create my custom SRV file. So I will make a new file in my SRV folder and call it turncamera.srv. For this project, I want to take in a number in degrees and return an image. So I will use float32 for my request and call the attribute degree turn. Then separate the request and response section with 3 dashes. Image. Now for the response, I will use the image message type from the sensor messages library. I will just call this response attribute camera image. Okay, with that, I can save this file and head over to my cmakeless.txt file. So here I will add my new service interface within the ROS IDL generate function. And of course, in the intro, I included sensor messages as a dependency. With that, I can save this file and I will go ahead and build our workspace. And open up a terminal. I'll go ahead and clear the screen. I'll change into my workspace directory, source it, and verify that our new interface was created. So here we see Udemy ROS2 package service turn camera. Great, now I can use this interface in my code. So I'll go ahead and minimize this and make my service server in our source folder. So I'll make a new file. So I'll just call it turncameraserver.cpp. As usual, I will just copy the service server code I made in the last lecture to use it as a baseline. I will go ahead and change the imported service to turncamera. I will also change the class, node, service topic, and callback function names to match the context of this project. I'll delete the current contents of the callback function. Then in my constructor, I can print out to my console that my turn camera service is running, which also means I need to import IOStream. Now remember, for this project, I just have 5 sample images which I'm going to choose from. So I'll make note of these values in a variable called available angles. I just noticed that my spacing is off. I will set this to tab and hit 2. That's better. So when I receive a request, the first thing I will do is check this list to see which number is closest to that of the number given by the user. So in my callback function, I will initialize a variable to hold the closest number between what the user inputted and the image numbers I have. I'll just initialize it as the first angle in the array. So I'm going to implement a for loop to go through each entry in the available angle array to find the angle closest to the one the user specified. So I'll create a for loop to go through every entry. Then I will calculate the angle difference by taking the absolute value of the difference between the degree turn attribute of our request within the current angle we are on. I'll need to make sure I initialize this variable, which I will do above. Then I will compare if this angle difference is smaller than the smallest calculated angle difference yet. Since I'm doing a comparison with this variable, I will need to initialize it with a value above, which I will just do with the first angle in the array. Then I will have one more variable which keeps track of the actual closest number in the array. So in my if statement, I will set these two variables equal to the values depending on what angle I'm on. Cool, so once this for loop finishes, then we should know which number in the available angles array is the closest to what the user gave in the request.
So the next thing I need to do is find the path of the corresponding image file. There are a couple ways you could have gone about doing it, but I'll just grab the workspace directory and navigate to the images directory, and then convert the closest num from a float to an integer so there are no decimals, and then convert it to a string to include it with the directory. Then finally the file extension is PNG. Now I need to somehow get this workspace directory, which I can actually do using the argv input from our main function. For now, I'll just go ahead and declare this workspace directory variable below within the private scope. Alright, now I can take in the first argv argument of our main function, which is a string that has the location of our executable, which if you run the executable through ROS2 run, will be deep within the install directory of your workspace class. You could test this out if you wanted by printing the argv entry out to the console, which you can try on your own. For now, I will pass it as an argument to our turn camera service class. Then I will modify the constructor to use it like so. So now I need to convert this executable file location into my image directory. So I will create another method of our class which will take care of this for us and set the workspace directory variable. Then I can define this function below in the private scope. This function will take in the exe directory, and I will find the index where the install directory location is. Then I will essentially delete everything past that index within the string to just get the workspace directory path. So now that I have my workspace directory variable filled, my image path should be correct. So for the sake of debugging, I will print out the image path so we can see it displayed when we make requests. Then I will create an OpenCV matrix variable to hold in the array of pixels from our image. In order to use OpenCV, I need to include it. Now, since I need to read in an image file, I will include the OpenCV image codecs header file. And I'll go back down. I will load in the image using the imread function, and I will pass it in the image path. You could have explicitly specified the type, but we can have C++ do it for us. If we hover over auto, it knows that the type this function is going to return. In this case, it is a OpenCV matrix object. Then I will convert the image we read in with OpenCV to a ROS image message, which I can do with the CVBridge ROS package, so I'll go ahead and include it. So I will be using the CVImage object from CVBridge. This takes in a header message, which comes from the standard messages package. And then the color scheme for OpenCV when it reads images in is blue, green, red, 8 image encoding. Then lastly, I will pass it in the actual image variable. Now, this is just the constructor for the CVImage class. To get the actual ROS image message, we have to call the toImageMessage method. Now, if I hover over auto, we can see this is a sensor messages image shared pointer object. Great. With that, we now have the image prepped to send in our response. So let's go ahead and wrap this up by loading in the response camera image attribute, in which I dereference the pointer we got from earlier. Great. That's it for the service server. So if we go back up to the top, we can see I declare our turn camera service node, pass it in the executable path, which it gets the workspace path from, starts my turn camera service, so that when it receives a request to turn the camera a certain amount of degrees, it will pick the image with the closest number to the user input value. Then we read in the image, convert it to an image message using CVBridge, and lastly set it to our response. Great, so be sure to save this file. So I'll head over to my CMakeList text file and add this new turn camera server executable, and target dependencies, and target link libraries to include the custom SRV file we made earlier. Be sure to include your OpenCV and CVBridge dependencies. Then be sure to add it to our install targets section. And with that, I can go ahead and save this file and compile it. Oh, and it seems the name I thought my node was doesn't match.
I'll just go ahead and rename this file for the time being. So the node name is turn camera service. So now it should match what I listed in my CMake list text file. So let's try and rebuild. All right, and this time I compile without any errors. Great. So let's go and test it out. So here we see our service node is running. So I can open a new terminal tab to make a request to it. Remember, you can use tab completion to help autofill these fields for you. And before I run this, if I go up to VS Code, I can actually go ahead and open up our ROS show status page. I don't know why it's doing that. And here we see our turn camera service node running, and we see our turn camera service. So after a while, a bunch of numbers flood the screen. Well, these numbers are the individual pixels of the image being returned to us. And it seems I made a bit of a typo here because we should have only seen one image path returned, which was this one, but instead we see the entire for loop going through its calculations and printing the images, which tells me that I may have left some code within the for loop which wasn't supposed to be there. So I'll go ahead and fix that really quickly. So go ahead and stop this, clear the screen. So only this content was supposed to be within the for loop, so I can take out this curly brace here. This way, the only thing we're doing in the for loop is finding our closest angle, and then the rest of the things only happen once. Okay, I'll go ahead and save that, rebuild it, just so that I can prove to you that this is working properly. And that's why we test these things, to make sure that we didn't make any mistakes. Try this out one more time with the same input. All right, so we still get the image pixels being returned to us, but here we only see one line saying that the closest input to the 0 input that we gave is indeed the 0th image. And I could change this to just double check that this is working as such. So I could put, say, 25. So in hopes we should get the 30-degree image. So if I send this request, we indeed get the 30 image. Cool, so I'll go ahead and clear the screen, stop the server. Well, it's no fun to look at numbers, so I will go ahead and start making my client so I can display an image based on what we receive back from the service server. So I will create a new file and call it turn camera client.cpp. And as usual, to speed things up a bit, I will copy my client code from the previous lecture and change the names from odd even check to turn camera and delete some of the code I'm not using. So I will go ahead and change the print statement to ask the user for a position input in degrees to turn the robot camera. And change the request to read in the degree turn attribute, which matches what we specify here in our turn camera SRV file. Then I expect to get returned an image message result, so I will use the CVBridge's toCVCopy function to convert the image message to an image, which can be used by OpenCV. Before I can do that, I will go ahead and include the CVBridge package. Now, this toCVCopy function takes in the image, as well as the encoding, which if you remember from earlier was BGR8. Great. Now I want to use OpenCV's image show function to display the image. But first I need to include my OpenCV dependencies. In this case, I need to include the hi GUI header files so I can use the display window functionality. Now I will go ahead and call the function on the image we got.
And I will use the wait key function, which set to 0, will wait for the image window to be closed, which you can do by hitting enter. And that about covers it. We create our service client, prompt the user via console to enter the position in degrees to fill the request with, then we wait for the service to become available, send an asynchronous request, and when we get a response message, convert it to an OpenCV image type and call the image show function. So I'll go ahead and save this file and head over to my cmakelist.txt file to make the executables. And add it to our install targets. So go ahead and save this and rebuild the project. All right, so it built successfully. So I'll head over to the terminal, rerun our turn camera service, and now we can run our client node. So here we get prompted in what degrees we want to turn the robot's camera to. I'll just give it something, say -17, which should return back the -15 image in our data set. And here we get an image returned to us, and if I actually scroll it down, we can see we were indeed returned at -15, and that it's displaying accordingly. And now if I hit the enter key on my keyboard, the image goes away. And we can test this out with different images. So for example, -35, we get the -30 image, and this is what it looks like. And I could try on the opposite end. I could try 27, and here we get the corresponding images. And with that, you have successfully completed this services project in which you implemented a ROS service to send a number we wanted our fake robot to turn its camera to. And since we don't have a real camera, we instead just returned a pre-taken image based on the request sent. You also learned how to incorporate the popular OpenCV framework into your ROS code to process and view image data. So I hope this gives you a little taste as to how you can implement computer vision in your robotics applications.